Welcome back to COSI 4755, 5755. Today we're going to talk about deterministic finite state automata. Up to now, we've only spoken about non-deterministic finite state automata. And I said earlier that they're equivalent, but I haven't explained to you how they're equivalent yet. So that's what the subject of today's lecture is. So first of all, what is a DFA? It's like an NFA, but it has tighter restrictions. Every state must have exactly one transition defined for every letter, and epsilon moves are not allowed. So let me give you an example of a DFA. If you look at this carefully, you'll notice that there is exactly one transition, or at most one transition, labeled by the same letter, leaving every state. So that's what makes it a deterministic finite state automaton. Now, the nice thing about deterministic finite automata is they're very easy to implement. Basically, all you need is some implementation of a table, so that given state A, you can just look up based on whatever symbol you're talking about what the next state to go to is. Now you see, of course, that you couldn't do this if for a non-deterministic automaton, because you'd have to put more than one letter in the same slot in the table. There are lots of implementations of DFAs, and they're very straightforward. Here's an example of one in Java where we have a two-dimensional table defined there, and then a short piece of code which does the simulation of the DFA. Very straightforward. The runtime of this piece of code is order m, where m is the length of the string. So remember, that's much better than NFAs. So we can speed up matching because in the worst case, NFAs with n states take order m n squared to match a string of length m. DFAs, on the other hand, take only order m. And there's another beautiful algorithm to convert NFAs into DFAs. So now in the overall context of what we've been talking about, using automata to do the lexical analysis for our compiler, we start with the lexical specification, right? So that's the file that's got a row for each lexical token, and then on each row there's a regular expression that defines what lexemes in the set of that correspond to that token look like. And then those regular expressions are converted into a non-deterministic finite state automaton in the way that I've already shown you. And then what happens in a tool like JFlex is that it's converted, the NFA is converted into a DFA, and the result is a piece of code that essentially simulates a table-driven deterministic finite state automaton. So here's how we can convert from an NFA to a DFA. Remember that NFAs can be in many states at once, while DFAs can only be in a single state at any time. A key idea in this simulation, we've already seen actually, is to make the DFA simulate the NFA. Remember, when we did the simulation, we had the states of the NFA. Essentially, we kept a set of states, which were all the places that the DFA could go to, or the NFA could go to. So what we'll do is we'll have the states of the DFA that correspond to the sets of states in the NFA. Transitions between states of the DFA correspond to transitions between sets of states in the NFA. So here's an example. Remember our automaton from last time, where we are simultaneously or in parallel accepting different token classes in our little example. We can convert this NFA to a DFA as follows. We start in the initial state, and remember, because of the epsilon moves, we automatically go to 1, 4, and 11 there. And so our first state in our DFA is 0, 1, 4, 11. right? So remember I said that the states of the DFA correspond to sets of states of the NFA. So there you go. There's the first state of the DFA corresponds to the set of states of the NFA 0, 1, 4, 11. Where can we go from state 0, 1, 4, 11? Well, we can just read that off of the NFA, and we see that with the D we can go to 2, 5, or 12, and then we have to deal with it to get state 11 to state 12 move. Then we can move on to the state 11 to 12 for everything other than a D, and that gives us a transition that looks like that, which of course is a compact way of writing what potentially could be a lot of transitions, right, for everything in the alphabet except for D. And then moving along in the simulation from 2, 5, and 12, where can we go? Well, with an O, we can go to 3, 6. Notice that the final states of this machine are any state in which one of the states of the NFA was a final state. Okay, and so then the rest of it's just the same as a DFA, so I just wrote it out there. We have to add just a little bit more here to deal with transitions out of these states for the other letters of the alphabet. Okay, so we convert that NFA to the DFA shown there. And of course, remember, we always want to label the final states with which token class they correspond to. And so I've done that there. So that's called the subset construction. And instead of marking whether a state is accepting, we just remember which token type is matched, right, with the color coding like I showed you on the last slide. We break ties with priorities like we talked about before. And when using the DFA as a scanner, we consider it to be stuck if it enters a state corresponding to the empty set, which was that state in the lower right-hand corner of the previous slide. Now, you don't get something for nothing in computer science, pretty much you never do. So there are some performance issues that we need to be aware of. The NFA to DFA construction can introduce exponentially many states. And so even though the DFA is very simple and runs in linear time, it might use a lot of space. It might use exponentially more space than the NFA from which it was created. Well, this should be familiar to you, the time-memory trade-off. I hope you've seen many times so far in your education here in computer science. So this is just one more example of it, where we have NFAs being low memory requirement, but taking a lot of scan time, and DFAs potentially requiring a lot of memory, but having very low scan time. Of course, it's possible, we won't talk about this, but it's possible to create a hybrid in which we simplify the NFA before we do code generation, or before generating the DFA, so that we get a more compact DFA. Okay, so that's it for this lecture. See you next time.